about the final project. We are going to explain about our final project, Human Emotional Recognition Benchmarking, a study of effective computing. We have a group of 6 members: Banu Prakash, Arsha Reddy, Likita, Sai Vikas, Satyakirti Dara, Venkata Naganjani. The main goals and the motivation of our project is to develop and benchmark the various machine learning models for the accuracy classifying human facial expressions. Models must categorize the image into one of the five key emotions, maybe happy, sad, angry, fear, or surprise. Our primary objective is like to conduct a robust comparison to determine the fast and effective strategy for high dimensional image data. We have a two approaches. Approach one relies on the, traditional feature training. It's on PCA and select k-best combination with the classical ML classifier. Another approach two on the modern deep machine learning methods by using CNN and transfer learning for automatic feature extraction. The goal of the project is to identify the solution that provides the generalization for the a production of ready to emotional recognition system. Next slide. The data set complexity and initial analysis, how we are going to analyze and how we are selected the data, we are going to explain this slide. The main core challenge of the data set is that to address the inherent complexity of the data, critical factor influencing the model selection and the performance. First one is scale and high dimensional. The size of the dataset consisting of 59,000 total of images. High D input, each dimension will be 128 into 128 images flattened, produce a feature almost of 49,000 plus, which is also a dimension of 128 into 128 into 3. Implications, how we are going to do that is that requires a aggressive dimensional reduction to make a classical machine learning model feasible. Then we are coming to a class imbalance. If anything class imbalance happened, what we are going to do? The five emotion categories are unevenly distributed. Example, happy is the largest class while surprise is the smallest class. The main risk in this is the imbalance introduce the complexity that can bias the models, leading to the lower performance on the minority classes. Then the pre-processing steps, what we are going to do that all the raw pixel values were scaled using a standard scalar. Then we're going to do the splitting in the category of 70 by 15 by 15 was used to ensure the class imbalance was accurately done. Yeah. Next slide will be explained by my one of my teammate.
Hi, my name is Kirti, and today I am explaining about the methodology. It is a three-pronged approach. In three-pronged, what is the methodological strategy? Is the project employs a three-pronged strategy to benchmark traditional feature engineering against modern deep learning for superior performance. We directly compare the efficiency and accuracy of methods that rely on manual feature reduction versus those that use automatic feature extraction. And the first pronged method is classical machine learning. In this, we trained on features that have been reduced to 49,000 down to 300 using PCA and select KWest. And our main goal is to evaluate traditional classifiers on statistically clean reduced data. And here we have used the models logistic regression and random forest and XGG boost. And the second approach is deep learning pipeline. It utilizes raw image data with the dimensions of 128 into 3 and complex architectures to learn features directly. Here, our goal is to leverage modern neural networks for state-of-the-art accuracy. And the models we have used here is custom CNN, convolutional neural network, and transfer learning model, fine-tuning a pre-trained network, and the exploratory sequence model. The third pronged approach is experimental, and it also has policy gradient. We use it for it. And our main model is here we used is reinforcement learning was used to explore the viability of framing the task as a contextual branded problem. And the second one is classical machine learning pipeline. here it is also called as feature engineering. How we featured it, the feature engineering imperative, due to the 49,000 features in each flattened image, direct training of classical models is infeasible. This necessitated a robust feature engineering pipeline to drastically reduce dimensionality while retaining critical information. The goal was to transform the complex image data into a clean, reduced, and standardized feature set suitable for traditional classifiers like logistic regression and XGBoost. And here the key dimensionality reduction steps is principal component analysis. Here we take action, configuration, and result. In action, we used PCA to transform the raw features into a new set of orthogonal components. In configuration, we configured to retain 95% of the total variance in the data. And in the result, we get the feature count was reduced from 49,152 to a maximum of 300 components. Our second step is statistical feature selection, the select k-best. Here we take the action to apply the select k-best after PCA, and our main goal is to further prune the 300 PCA components, selecting only the subset with the highest statistical relevance. This prevents noise and improves model generalization. For the outcome of these classical models is this is a two-step process, provided a highly optimized input for the classical ML models, allowing them to train efficiently and effectively on a feature set that is rich in information but manageable in size. Next slide will help. Will be my friend will explain.
Hello everyone, my name is Banu Prakash. Today I am telling about the architectures which we use in using deep learning. So coming to that automatic feature extraction, the model which we use, it bypasses manual feature reduction like PCA, select k-based by using layers designed to automatically learn features from the raw 128 120 by 128 image data. And coming to the custom convolution neural network, the design which we use is standard architecture with alternating convolutional layers, feature mapping, and pooling layers. It's downsampling. And the function of it is it learns the complex and hierarchical spatial patterns, edges, features directly from pixels. And coming to the output, which we get is a finite dense layers and a softmax classifier. And transfers learning hits a mobile net v2, and the strategy is used as utilize a pre-trained mobile net v2 model as a powerful feature extractor. Adaptation, the mobile net v2 base weights were frozen, and a simple custom classification head was added and trained for the five emotion classes. And the benefit of it achieves high performance efficiency, leveraging external knowledge. And recurrent neural network purpose is exploratory model training image rows as sequence, and the mechanism used a long short-term memory layer to capture dependencies across the rows of the image data. Coming to the next slide, complexity of the hyperparameter tuning. Optimization is complex. Optimizing model purpose requires systematically searching for the best hyperparameter settings, which differ significantly between classical and deep learning models. Classical model tuning is the first one. We use the model is a random forest classifier, and the method used is random classifier search EV to efficiently sample and final optimal values for parameters like tree depth and number of estimators. The goal, achieve the best fit on the PCA reduced features. Deep learning optimization. Deep learning introduces great complexity, uh, requiring fine-tuning of architectural and training load for parameters. Key parameters include learning rate, batch size, and number of epochs we are optimized. And overfitting management, crucial callbacks were implemented to manage the long training process. Early stopping automatically hits training when validation loss stops, improves preventing overfitting. Learning rate reduction reduces the learning rate when performance fluctuates, helping the model coverage to a better solution. And my friend will explain the next one.
Hi, my name is Vikas, and I'm gonna explain the classical models performance. Classical models after applying our feature engineering pipeline. The random forest performed the best with 83.34% accuracy, which became our benchmark. This strong result mainly came from using PCA and select K-best, which reduced the image from tens of hundreds of pixels to a small set of meaningful features. Because of this, the tree model were able to capture the nonlinear patterns in the data very effectively. Linear models like logistic regressions struggled because emotions in faces are not linearly separable. Overall, with the right features, classical models gave us high accuracy, trained faster, and needed less computational power compared to deep learning. And let's come to the next slide. And here we're going to talk about the deep learning and RL performance issues. This slide shows the challenges we faced when reinforcement learning models. Our best CNN reached only around 55% accuracy, much lower than the classical models. We also noticed a high validation loss, which means the models were not learning strong or generalizable features. One key feature, one key reason is that pre-trained networks like MobileNet V2 didn't transfer well to emotion-focused data, and limited fine-tuning made it harder for the model to adapt. And the hyperparameters such as learning rate and batch size may also have been suboptimal. In summary, the deep model underperformed and improvements like better argumentation, deeper fine-tuning, and more systematic hyperparameter tuning are needed for them to catch up the classical approach. And thank you. Like my friend gonna cover the next slides.
Hello everyone, my name is Harshavardhan. I'm going to explain in-depth analysis classifications. Why did the classical models win? In this project, outcome is highly inconvenient and the deep learning typically dominates complex image tasks. The results point to critical success in future engineering and the identifiable limitations in the deep learning pipeline. Coming to success of manual future engineering, there are two types of manual future engineering: the future optimization and the non-linear modeling. A future optimization, the combination of PCA and select K-best, and the non-linear modeling. This clean reduced future set was exceptionally discriminative, allowing the powerful tree-based assembles like random based and XSB boost, XGBoost, and to easily model the complex and the nonlinear relationships resulting in the 83.34 accuracy. Coming to deep learning pipeline limitations, those are three types of there are different limitations in these. So convergence, failure, dominance shift, architecture mismatch. Coming to convergence failure, deep learning models like exhibit high loss values indicating poor convergence and the inability to learn effective features automatically. Dominance shift, the pre-trained weights of MobileNet V2 did not translate well to specific standardized emotion data, highlighting a domain mismatch that hampered its future extraction ability. Architecture mismatch, the low performance of the custom CNN suggests that architecture's hyperparameter configuration was suboptimal for the dataset, failing to learn the correct spatial patterns. Conclusion: the random forest model trained on a PCA select best features is the clear optimal choice, offering the highest accuracy, supervisor computational efficiency, and the ease of deployment compared to struggling neural networks. Coming to next slide, per class performance and confusion analysis. This slide uses the confusion matrix of the random forest classifier to analyze where the model excelled and where it struggled, providing granular insight into the emotion classification. Granular accuracy, where the model excelled, analysis of diagonal values in the collision matrix shows the model was highly successful at the classifying specific emotions, happy and angry. Happy means this was the easiest and the most accurate class due to the large sample size and the distinct facial features achieving near perfect prediction. Angry classified very well, suggesting that the distinctive furrowed brow and the tightened mouth features were the successfully encoded by the PCA select K-based features. Key misclassification areas. The off-diagonal elements of the matrix reveal which emotion pairs were the most difficult for the model to distinguish. Sad versus fear. This was the most common confusion pair. Both emotions can involve wide eyes or a downward turn of the mouth, making separation challenging even with the optimized feature set. The model often mistook instances and fear for sad. Surprise misclassification. The minority class surprise was occasionally confused with happy or fear, like due to the presence of wide open eyes in all three expressions. Coming to conclusion on generalization. The random forest model demonstrated strong overall generalization, 83.34 percentages, but this analysis highlights that future work must specifically target the features that differentiate subtle high confusion pairs like sad, fear, and surprise to push accuracy higher. Coming to next slides, my friend Anjani will continue.
Hello, this is Anjani. So, coming to the computational cost and efficiency, this slide addresses the practical implications of the results, focusing on the differences in computational cost and efficiency between the successful classical pipeline and the deep learning models. So, the production ready choice is the random forest. It has 83.34 percentage of success rate on PCA reduced data is the optimal production solution based on a cost benefit analysis. So it has the highest accuracy and the low inference latency and the minimal hardware. So coming to the conclusion, the project demonstrates that in case where manual feature engineering can create a highly discriminative low dimensional feature set, classical and ensemble methods can provide superior accuracy and vastly better computational efficiency than struggling deep learning architectures. Coming to the next slide. Addressing limitations and future work. Identified project limitations. Deep learning failure. All neural networks severely underperformed the random forest model. The reason is high loss and poor convergence point to inadequate hyperparameter tuning or suboptimal architectures. And the one is the domain mismatch. The low accuracy of mobile net v2 suggests its image net train features did not transfer effectively to our specialized emotion dataset. Class imbalance. Although stratified, the large difference between majority, that means happy, and minority classes like lower recall on emotions like surprise and fear. So, future work and enhancements. Deep learning reoptimization. Implement automated hyperparameter tuning to find a robust CNN architecture. Introduce data augmentation to increase training data variability for better generalization. Addressing imbalance. Use techniques like SMOTE for the classical pipeline. Apply weighted loss functions in deep learning pipeline to specifically improve accuracy on minority classes and advanced transfer learning. So experiment with unfreezing later layers of mobile net v2 for file tuning, better adapting its features to our specific emotion data. Coming to the next slide. Overall conclusion and recommended solution. So project conclusion is the comprehensive and comparative benchmarking yielded a surprising but definitive result. The classical machine learning pipeline decisively outperformed all deep learning models. The random forest classifier achieved the highest overall test accuracy at 83.34%. The best performing deep learning model only reached 55.07%. So the optimal production ready solution is for real world deployment is a random forest classifier trained on feature engineered data. So as it gives the highest accuracy, computational efficiency, and minimal overhead, random forest is considered as the optimal solution. So this project demonstrates a critical lesson. When manual feature engineering successfully extracts a highly discriminative and low dimensional feature set, classical ensemble methods can provide superior and more efficient solution than poorly tuned or mismatched deep learning architecture. So the code will be shown by my friend Likita, and this is the end of the presentation slides.
Kirti, can you share the screen of the code? Uh, what are the things we are implemented and everything. I'll gonna explain how we implemented the code and everything. Mainly our code implementations consisting of a facial uh, emotions recognition system during the classical machine learning, deep learning, and reinforcement learning technique. It begins by importing all the required libraries and fixing the random seeds to ensure the reproducibility, and the dataset loaded from the structured emotion folders, image parts, and the labels stored in a dataset frame. A random sample images displayed for the verifications. All the images was resized into 128 into 128 dimension for the normalized, converted into numpy arrays, and saved the avoid the repeated processing. That labels are encoded numerically and data is split into a training, validation, and testing the facial things. And data argumentation is applied to improve the model generalization. For a classical model, that images are flattened and standardized and reduced using PCA, and the most important features are selected using a select kbest. For the logistic and XBoost and the random forest models are then trained and evaluated using the accuracy and the classification reports and saved. For the deep learning, the three neural networks are implemented using a custom CNN trained under Scratch, and the mobile net V2 transfer learning, a model using a ImageNet for the RNN with the LSTM, and all the trained using early stoppable learning data scheduling, then evaluated and saved. Reinforcement learning is also applied in the reinforcement policy grant algorithm when the models are learned to predict the emotion based on the rewards of a correct predictions. Finally, all models are evaluated using the accuracy and the classification report confusion matrix and the training performance graphs to compare the effectiveness and the train models to save the future deployment. This is about the code details and everything. This is how you can see this on the screen: fear, sad, angry, happy face, and everything are implemented using those things. This is about our code. Thank you.